Welcome back everyone, Patrick here, moving on to another question dealing with triangles. So we are given the triangle A, -3 and 1, B 2 and 5, and C 5 and 1. And we have to find the midpoints of each of the sides, and then we have to create a medial triangle, which is basically the triangle that's created when you join all of the midpoints. And I'm going to go over that a little bit generally before we get into the actual algebra in a second. Then part B, we have to verify that that medial triangle is going to be similar to triangle ABC. I'm going to go over what that means as well. And then part C, we have to verify that the area of triangle ABC, the larger triangle, is 4 times the area of the medial triangle. So that's actually a property, that the area of a large triangle is always going to be 4 times the area of the medial triangle, no matter what kind of triangle you draw. It doesn't have to be necessarily these coordinates. So again, first I want to go over some of these concepts a little bit in general before getting into the actual algebra. So let's first talk about what a similar triangle means. And similar triangles, there's actually going to be a whole section on that, so I'm only going to go over this briefly, whatever is needed in this particular question. And a similar triangle, or 2 similar triangles, let's say we have a triangle like this. One way to look at it is basically it's going to be another triangle that has the same angles as this one. So it could be like zoomed in or zoomed out. That's the way I like to think about it. So for example, let's say that this triangle here, this angle is like 50. Let's say that this angle here is going to be, let's say it's 60. And then that's what, 110, so this would have to be 70. Right? Let's say we have a triangle with those angles right there. Well, a similar triangle can be a triangle that's much smaller than this, but it has those same angles. So let's say that we have another triangle that looks like this, so it's 50, 60, and then 70, like that. So if they have the same angles, these two are similar triangles. Another thing I want to mention is that a lot of times it's not going to be in line like this, so we could take this triangle and we could flip it over. Right, we could shift it left and right, so this could be maybe like, let's say 70, 50, and then 60, right? This triangle is still similar to this one, right? All of the angles are still going to be the same, so it's not always going to be nicely in line like this, and actually when we're dealing with the medial triangle, it's not going to be in line, it's going to be flipped over and stuff, so I'm going to show you that in a second, but I just wanted to mention that with similar triangles. Now, angles is one way to look at them. If all the angles are the same, it's a similar triangle. But another way to look at it is to actually compare the side lengths. And with the side lengths, and that's what we're going to be doing in this question, basically if the side lengths have a common ratio between them, from the smaller triangle to the larger one, or vice versa, if the ratio is common for all 3 sides, then it's a similar triangle. And what do I mean by a ratio? So let's say that this triangle here, let's say it has lengths, I don't know, let's say 10, 8, and then let's say 12 over here. And then let's say that this triangle here, it has lengths 5, 4, and 6. Notice that the ratio between each of these sides is the same. So notice that 10 over 5, right, it's equal to 12 over 6, which is equal to 8 over 4. And the ratio of all 3 is basically going to be 2, right? All of those equal 2. You can also flip it, so we can say 5 over 10 equals 6 over 12, which is equal to 4 over 8. And notice that the ratio of all of these simplifies to 1 over 2. Okay, and 2 and 1/2 is just one kind of ratio, right? This could have been maybe like, let's say, I don't know, like 15, 12, and then 18, right? And then notice it'd be 15 over 5, which is 3, 12 over 4, which is 3, 18 over 6, which is 3, right? So that ratio would be common. And then let's say that we had 15, 12, and then let's say over here we had 12, for example. Well, then these two triangles are not similar because we have a ratio of 3, right? 15 to 5, 12 to 4, but then 12 to 6 is a ratio of 2, right? The ratio of all three sides has to be the same for the ratios that relate both triangles in order for them to be similar. And as I mentioned before, this triangle here, it could be flipped over, rotated in different ways, right? It doesn't have to be exactly in line like this. But if you do see that pattern where the ratio of all the sides is going to be the same, right? Sometimes you got to kind of match them, right? When you flip it over. And the way it's going to match, especially if it's a scalene triangle, well, in this case, actually, it's an isosceles, but if it's a scalene, well, you just match the largest side to the largest side, the smallest side to the smallest side, the middle side to the middle side. And the ratio, no matter which way you flip it, should be the same for all three sides if the triangle is going to be similar. So now, how is all of this going to relate to the medial triangle that we're going to work with in this video? So just in general, a medial triangle, if we draw a large triangle like this, we can maybe even make this the official triangle. Yeah, sure, why not? So we'll let this be A, this would be B, this will be C, like that. What we have to do, what we're going to do in part A is we're going to find all the midpoints of all the sides. So we're going to find the midpoint here, we're going to find the midpoint here, and then we're going to find the midpoint right there. And then what's going to happen, we're going to join those midpoints, okay, and we're going to get this triangle right here. So this triangle, that's called the medial triangle. And again, this could be all different kinds of shapes and sizes. So like if we have a triangle, maybe, let's say we have an obtuse triangle, right? The medial triangle would look something like that, for example. Okay, so these properties of similarity and then this area being 4 times, right? The larger area being 4 times the area of the medial triangle, it's going to apply for any kind of triangle. I'm just keeping the diagram like this just for simplicity for the explanation. So this is going to be the medial triangle here. Now, how are we going to show that it's similar? Well, if you remember in a previous video, we talked about the triangle midpoint theorem. And what did that theorem state? Well, it stated that, let's just deal with this line here, and then let's label this midpoint of AB, let's label that X, this midpoint of BC, let's label it Y. What we stated was that this, or what we showed, was that this side is always going to be parallel to this side, and it's going to be half the length, or this length is always going to be double this one. We went through that in a previous video, the triangle midpoint theorem, right? On the website, if you want to go through that video and find it, make sure you watch that before watching this because the concepts are going to carry over. So this length is half of this length. Okay, so if we, let's maybe label these. So if we, let's say we label this length here, let's label it 2m, this length right here. It means that this length over here is going to be m, right? It's going to be half of that right there. Right? We could also label this m, and we could label this half m or 4m and 2m. I'm just going to keep it as a 2m and m, just to keep it simple with no fractions. So that's only these two midpoints, but it applies for any midpoints that you join. So if we let this midpoint, let's let it be z, that means that the line xz it's going to be parallel to this line, BC, and this length is going to be half of this length. So if we let this length here be, let's say 2n, right? A lot of letters here. Right? This is going to be 2n. Then it means that this length over here is going to be n. Okay? And then this side, this length over here, it's going to be parallel to this side AB. If this has a length of O, right, then this whole length is going to be 2O. Right? So no matter what triangle you draw, this is always going to happen. So basically these sides in the medial triangle are always going to be half the length of the sides of the larger triangle. And then going back to when we talked about similarity, it basically means that the ratio of all the sides is going to be the same, right? Because we're going to end up with 2m over m, and then we're going to end up with 2n over n, and then we're going to end up with 2o over o. Notice that all of these cancel, 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 and we're just going to end up with 2 over 1 in all of these, and the ratio is going to be 2. Or if we flipped it over, it would be 1 over 2. And so that's how we can show that the triangle is going to be similar. We can find the lengths of AB, BC, AC, then we could find the lengths of the medial triangle, and we're going to see that the medial triangle, the lengths, all of the lengths are going to be half of the lengths of the larger triangle. And then from there, we prove that it's similar, right, according to how we explained similarity before. Right, so this might be a little bit of overkill in terms of explaining before we get into the actual algebra, but just want you to have a high level overview of what's happening. And what I'm explaining here, this ratio of 2 between the sides of a large triangle and its medial, or of any triangle and its medial triangle, it's always going to be 2, no matter what you draw. And then if you could just show that with all the side lengths, you're always going to show that the two triangles are going to be similar. And then in part C, what we're going to do is we're just going to find the area of the large triangle, find the area of the medial triangle, and you're going to see the area of the large triangle is going to be 4 times the medial triangle. And again, not just for this triangle, for any triangle, this property is going to hold. So let's get into the actual question. So let me draw a new triangle over here. So we'll have A, -3 and 1. Over here we'll have B, 2 and 5. And then we'll have C over here being 5 and 1. And actually, if you draw this on a Cartesian plane, it's actually going to have this kind of shape because these two y values, the 1 and the 1, they're actually the same. So this line here, it's actually just going to be a horizontal line. And I wanted to keep it like that for this question, really for part C, so we can get through that area a little bit more quickly. Because really I'm just trying to focus on the properties of the medial triangle in this particular video. We've gone through videos of where we had to find more complex areas where the triangles were like rotated. We had to find altitudes and stuff. And you might run into a question like this where you have to do that as well. But in this case, I just kept the triangle like this just to have that area be an easy calculation, because then finding the base and then finding the height is just going to be straight down. Right? The height is actually just going to be 5 minus the y value of 1. The height is going to be 4 over here. But we'll discuss that once we get to part C. So the triangle, the actual coordinates in this particular video, they're going to be pretty simple to deal with. So let's find these midpoints over here first. So let's find this midpoint. How do we find a midpoint? Well, we would add the x values and then average them out, divide by 2, and then average out the y values and divide by 2. So we would have -3 plus 2 dividing by 2, and then we'll have 1 plus 5, and we're going to divide by 2. So this would end up being what? Negative 3 plus 2 is negative 1. That's going to be over 2. 6 over 2 would be 3. So this midpoint here, it's going to be negative 1 over 2 and 3 like that. This midpoint over here, add up the x value, so 2 plus 5, which is 7, divide by 2, then 5 plus 1, that's going to be divided by 2, so that's going to give us 7 over 2, and then this would be 3 again, right? These lines are going to be parallel to this line, meaning that those y values are also going to be the same if you actually draw this on a Cartesian plane. And then over here, this midpoint, add up those x values, so we'll have negative 3 plus 5, we're going to divide that by 2, and then we'll have 1 plus 1, and then we'll divide that by 2. So negative 3 plus 5, which is 2, that's going to be divided by 2, and then we'll have 1 plus 1, which is 2, that's going to be divided by 2 as well. So the midpoint actually is just going to be 1 and 1 over here, right? Yeah, it's going to be 1 and 1. That y value is going to stay the same, right? So those are the coordinates of the medial triangle. So that's what we had to do for part A, and then what we do is we basically join those to create that medial triangle. So now let's move on to part B, where we verify that that medial triangle is going to be similar to the larger triangle. So this is going to take the most time, part B, because we're going to essentially find 6 different lengths, right? The 3 lengths of the larger triangle, then the 3 lengths of the medial triangle, and then we got to show that the ratios are going to be the same. So the length formula, just in general, it's what? It's the square root of x2 minus x1 squared plus y2 minus y1 squared. So let's actually label these midpoints. So x, y, and z. Okay, so we have something to refer to. So I'm going to find the lengths of the larger sides first. So let's start with AB. So we'll let this be x1, y1, x2, y2. So we would have x2, which is 2, minus x1, which is negative 3. That's going to be squared, plus y2, which is 5, minus y1, and then that's going to be squared. So we would end up with 2 minus negative 3 is like 2 plus 3, which would give us 5. Be careful with your negatives here. 5 minus 1 is 4. These are still going to be squared. We'd end up with 25 plus 16, which would give us root 41. Okay, so let's keep track of these over here. So the side length of AB is root 41, and I'm going to keep this as an exact value in case your teacher wants you to work with exact values. So then we're going to show how one of the lengths of the medial triangle, remember it has to be half of this, so we're going to show that it's going to be root 41 over 2 with this kind of algebra. But if your teacher allows you to work with decimals, they don't really require exact values. You can just get the decimal of this, and then you could get the decimal of the smaller sides we're going to find, and then just compare those decimals. But in case they're a little bit more picky, I'm going to keep everything as an exact value just because it's tougher to work with than decimals. All right, so that's A, B. So now let's find B, C. And B we already have labeled x2, y2, so I'm going to label C as x1, y1. Right, so what would change is this coordinate, that's going to be the x1, and then this coordinate, that's going to be the y1. So the x1 is 5, and then the y1 is 1. Right? And then the x2, y2, it's still staying the same for B. So over here, we'd end up with negative 3 squared plus 4 squared, which would give us 9 plus 16, which would give us 25. Square root of 25 is just 5. Okay, so BC has a length of 5. Right, and then what's left to find is AC. So we just use C as x1 and y1, so I'm going to let A be x2, y2. So we're going to be subbing in here. Right, so we would have -3 minus 5, and then we'll have y2, which is 1, right? Yeah, and then that's going to be, right, the y values are the same, -1. So this is actually just going to be 0. In fact, because we said this is going to be just a horizontal line on the Cartesian plane, you could just look at the difference between the x values, right? From -3 to 5, that's a length of 8. But if you want to show it algebraically, this would be 0. We'd end up with -8 to the power 2, which would give us 64. Square root of 64 is 8. Right, so AC has a length of 8, like that. Okay, so those are the side lengths of the larger triangle. And now what we got to do is we got to find the side lengths of the medial triangle, of the smaller triangle, and then see how those side lengths compare to the side lengths of the larger triangle. So first I'm going to find the length of XZ. So let's label this x1, y1. This will be x2, y2. Again, it doesn't matter which one is x1, y1, which one is x2, y2. You're going to get the same thing. And over here, we're going to be dealing with fractions and negatives. So let's just be super careful. So we'll have x2, which is 1, minus x1, which is -1/2. Put that in brackets. That's going to be squared. Plus y2, which is 1, minus y2 minus y1, which is going to be 3. Sorry. Right? x2 minus, okay, so we're all good here. So what would end up happening here, this would end up being 1 minus -1/2 would end up being 1 plus 1/2. This 1 over here, we can multiply this by 2, multiply this by 2, so 2 over 2 plus 1 over 2, which would end up being 3 over 2. So this would end up being 3 over 2, that's going to be squared, plus -2. And then that's going to be squared, like that. And then, remember when you have a fraction to an exponent, we could take the numerator to that exponent and the denominator to that exponent. So that would give us 9 over 4, like that. So this would end up being 9 over 4 plus -2 to the power 2 is just 4. So that's like over 1. So we could multiply this by 4, multiply this by 4. So continuing to simplify this, be careful with the fractions here. We'll have 9 over 4 plus 16 over 4, which would give us 25 over 4. That's going to be square rooted. And then if you're square rooting a fraction, the whole fraction, you could square root the numerator and then the denominator. So we could square root the 25, square root the 4. What do we end up with? 5 over 2, or 2.5. So that's the length of xz. It's going to be 5 over 2. And notice how that makes sense according to that triangle midpoint theorem, because remember, xz has to be half the length of BC, right? Notice BC is 5, and we just found that xz is 5 over 2, or 2.5, half of BC. Okay, and actually let's just line these up. So I'll put xz in line with BC, like that. All right, so we found the length of xz. So now let's find the length of xy. And notice this length is easy to find because of the same y values. On a Cartesian plane, it's just going to be a horizontal line. So when we subtract the y values, that part's going to be 0. So really, it's the difference between 7 over 2 and -1/2. So if we do that, what's 7 over 2 minus negative a half? Well, that's going to be like 7 over 2 plus 1 over 2, which would give us 8 over 2, which would give us 4. So the length of xy is actually just going to be 4. And if you did this, right, you would put that in the bracket, square that, but then square rooting it, it would cancel out that exponent and you'd just end up with 4. Right, so the distance from negative a half to 7 over 2, or from negative 0.5 to 3.5, if you want to look at it in terms of decimals, is going to be 4. So the length of xy is 4. Notice how that's half of AC as expected. So xy has a length of 4. And then finally, what's left to find is the length of yz. YZ, so I'll let this be x1, y1, I'll let this be x2, y2. Okay, so let's be careful with the fractions here. So we'll have x2 minus x1 squared plus y2 minus y1, and then that's going to be squared. So what would end up happening here? 1 minus 7 over 2, that's like 2 over 2 minus 7 over 2, which would give us negative 5 over 2. So that would be negative 5 over 2, that's going to be squared, plus 1 minus 3 is just negative 2, and then that's going to be squared, like that. And then from here, negative 5 over 2 squared, that's like negative 5 squared, put that in brackets, 2 squared, like that, negative 5 to the power 2, 25, 2 to the power 2 is 4. So we'd end up with, 25 over 4 over here, plus 4. That 4 is going to be over 1. So that's like, if we get a common denominator, multiply by 4, we'll have 25 over 4 plus 16 over 4, which would give us the square root of 41 over 4, right? And then we could square root the numerator, square root the denominator. So we'd end up with root 41, root 4 is 2, like that. As expected, this was root 41. The length of AB was root 41. Notice that the length of YZ is root 41 over 2, half of that. Okay, and we showed it with exact values. That's how you show with your exact values, in case your teacher wants you to do that. But again, you can also just get the decimals of those if you want, and then show that they are half as well. Okay, so we found all the lengths, and notice that now we can compare the ratios. Right, so if you want to show it like in a proper format, you could say root 41 over root 41 over 2. That's going to equal 5 over 5 over 2, which is going to equal 8 over 4. And all of these is just going to be 2. Right, this root 41 is like over 1 divided by root 41 over 2, which is like root 41 over 1 times 2 over root 41, and then notice the root 41s. They're just going to cancel out. We're just going to end up with 2 over here. Same thing here, 5 over 1 divided by 5 over 2 would be like 5 over 1 times 2 over 5. The 5's cancel out, we end up with 2. 8 over 4 is 2. All the ratios are 2, or if we flip them over, they would be 1/2. Either way, the ratios of all the sides are the same between the larger triangle and the medial triangle, and so we showed that the two triangles are similar. And now finally, part C, we got to find the area of both triangles. And as I mentioned, the area, it's going to be easy for both just because of the way the points are organized. So let's start, first off, area in general is what? Base times height of a triangle divided by 2. So if we draw that larger triangle, if you actually draw this on a Cartesian plane, so we'll have -3 and 1 5 and 1. Okay, so we'll use this as the base, and we know that the base AC has a length of 8. Okay, what's the height going to be? Well, because this is just a parallel, or not a parallel, or a horizontal line, and then this point has a coordinate of 2 and 5, basically this line, the length of this line over here, it's just going to be the difference between the y values. Okay, that's not always going to happen, so if this was like shifted, then it would be a lot more complex. We got to do the whole altitude thing, which we've done in videos before. But in this particular case, just because of the way the triangle is given, we're lucky that those y values are the same. So this is a horizontal line, meaning that this line here is basically going to be, the length of this line is going to be the difference between the y value of this point, of the top point, and the y value of all of these points. And it has the same y value of 1. All of these have the same y value of 1. So it's just going to be 5 minus 1, which is going to be 4. And so we'd end up with a base of 8, a height of 4, dividing by 2. 8 times 4, 32, divided by 2, 16. Okay, so the area of the large triangle is 16. What about the area of the medial triangle? Well, same thing, it's just going to be flipped over. So this here is going to be a horizontal line on a Cartesian plane because those y values are the same, 3, right? And so we would have, let's just label these, -1 over 2 and 3. We'll have 7 over 2 and 3. And then this point down here is 1 and 1 like that. So this base, if we let this be the base of the triangle, that's xy. Xy has a length of 4, right? This length over here is 4, the difference between the two x values. And then the height over here, because this is a horizontal line, the height is just basically the difference between these y values and this y value. So the height is just 2, like that, right? The difference between 3 and 1, right? Just the difference between the y values of this point and any of these points right here. All of these have the same y value of 3. 3 minus 1 is 2. So in this case, we have an area with a base. The base is 4, the height is 2, divide by 2. Notice the 2's cancel out. So the area of the small triangle is equal to 4. And so we confirmed, we verified that that large area, the area of ABC, is 4 times the area of the medial triangle of the smaller triangle, X, Y, Z. Okay, again, the area calculations in this case were simple because of the way the triangle is organized, but it could be any triangle. So you can go through that very long process, right? If you get a more complex triangle where you got to find the altitude for the height, find the distance or the length of the altitude. Even if you go through all that crazy stuff for any triangle, you'll always notice that the larger triangle area is 4 times the area of the medial triangle. That's going to hold for any triangle. All right, so that's it. Just some properties dealing with a triangle versus the medial triangle.